Welcome to the video summary series for Padisco's Introductory Statistics textbook. In addition to chapter summary videos such as this one, Introductory Statistics also offers podcasts, virtual tutor e-learning, homework activities with anti-cheat and auto-grade functionality, and detailed instructor resources. Find out more at padisco.com/introstats. For now, over to the author.
Hi again, I'm Sean Thompson and welcome to the next summary in the Padisco Statistics video series. This summary is about sampling distributions. In particular, we'll be going over the behaviour of samples, the sampling distribution of the mean, the sampling distribution of the proportion, and sampling distributions and inference. We'll start with behaviour of samples. If you're trying to discover something about a population, we've said a few times in this series before that what you do is you collect and measure a sample. For example, suppose millions of kids from across the country have just done a general aptitude test. This effectively produces millions and millions of test scores, an entire population of test scores. A small academic team wants to study the results, but they don't have the resources. Knowing the population mean score in the test will help the team out, but they can't calculate this without all the scores in the population. So they collect a sample of, say, 100 scores and calculate a sample mean. But why is there a connection between the sample mean and the population mean? If the team went out tomorrow and collected a different sample, they'd almost certainly get a different sample mean. There are in fact many different sample means they could calculate depending upon which one of the many different samples they happen to collect. So why should sample means be trusted to tell us anything about population means? Well, there are two basic reasons why. First, while sample means from a population do vary, they vary around the population mean. Second, they don't vary much. So the idea is that any sample mean you collect is going to be not too far away from the population mean. Now, this is all a bit fuzzy and we'll make this more precise later in the video. But for now, the important thing to consider is that if we start off with a population X of numbers, there's actually a whole population of potential sample means you could calculate from X. And this population is denoted X bar, and the sampling distribution of the mean is the probability distribution that describes X bar. In simple terms, what this means is that we're studying how sample statistics, like the sample mean, behave. What sort of sample means could you get from a population? How likely are they? How much do they vary? Now, in talking about the behaviour of samples, we've already started getting into the sampling distribution of the mean. But that's okay. The sampling distribution of the mean is one of the most important ones there is. To emphasise the important points we've already made, and to make them more precise, we're in a situation where we have a population X. Let's say for the moment X has this distribution. We've given it a normal distribution for the moment, and we want to know the population mean, mu. We might collect a sample of values from the population and calculate a sample mean. Of course, if someone collected another sample, they would get their own sample mean. And so there is a whole set of possible sample means we could get. And this set is what we denote by X bar. And the point is, these sample means follow their own distribution, the sampling distribution of the mean. So what sort of distribution is this? Well, as we mentioned earlier, the sample means will centre on the population mean, mu. In more precise terms, this means that the population mean of X bar is the same as the mean of the original population X. Also, sample means don't tend to vary much. In fact, if your original population X has standard deviation sigma, and you're drawing samples of size n, then X bar has a standard deviation of sigma on the square root of n. In other words, the larger the sample size is, the less and less sample means vary about the population mean. In terms of the actual shape of the sampling distribution, if your population X is normal, then so is the set of sample means. But even if X isn't normal, X bar will still be approximately normal, provided your sample size is big enough. The sampling distribution of the mean is the main sampling distribution we look at for numerical variables. If we have a categorical variable, we look at the sampling distribution of the proportion. If your variable X is a categorical variable, then that means its values are categories. For example, suppose you're looking at people's favourite ice cream flavour out of chocolate, strawberry or vanilla. Then those three flavours are the three categories of X. And you'll often be interested in the proportions for one or more of those categories. For example, you might be interested in chocolate and maybe 40% of people choose chocolate as their favourite flavour. So the population proportion for that flavour would then be 40%. We often denote the population proportion by the symbol pi. Now, like with the sample mean, you can collect samples from the population and calculate a sample proportion. And if different people collect different samples, then they would get slightly different proportions. One person might get 42%, another person might get 39%, and so on. But again, these sample proportions probably tend to centre around the population proportion. So like we did with the sample mean, we can define a new variable, which we call p, which represents all the different sample proportions you could get from the different samples that could be collected. The sampling distribution of the proportion is the probability distribution for this variable, p. Now, as I just mentioned, we'd probably expect that these sample proportions to hang around the population proportion. And that is true. To put it technically, suppose you've got a categorical variable x and you're interested in a particular category within x that has a population proportion of pi. You denote by p the sample proportions for this category for samples of size n. Then p will approximately follow the normal distribution with a mean equal to the population proportion, pi, and a standard deviation given by this formula. So we've covered the second big sampling distribution, the sampling distribution of the proportion. We'll spend the rest of this video talking about how sampling distributions are used in statistical inference, because we actually want to use all this stuff so that we can collect a sample and then conclude things about the population. So how do we do this? Well, what I'll do is discuss an example that is covered at length in the PDISCO textbook to give you an idea of how sampling distributions help in inference. Suppose you have a friend who has written two computer programs, and one spits out numbers from population X, which is normal, with a mean of 50 and a standard deviation of 5. The other program spits out numbers from population Y, which is normal, with a mean of 55 and a standard deviation of 30. Your friend gives you a sample from one of these two programs, but you don't know which one. Now, the sample has a mean of 52, so which population do you think is more likely? Here's an image showing the two populations, X and Y, with the sample mean of 52 marked. Notice 52 is closer to 50, the mean of X, than to 55, the mean of Y. Does that mean we should guess X? No. Let's look at the sampling distributions instead of the original populations, because the sample mean of 52 is technically a value in one of these sampling distributions. Now, the sampling distributions are actually very different to the original populations. The scale has changed enormously on these diagrams. The sampling distribution of X is normal, with a mean of 50 and a standard deviation of 0.5. And the sampling distribution of Y is also normal, but it has a mean of 55 and a standard deviation of 3. Now, our sample mean of 52 came from one of these sampling distributions. Looking at them, which one do you think it is? If you now guess population Y, you'd probably be correct. The two sampling distributions tell you what sort of sample means you would collect from the two populations. 52 looks extreme in X, but not so extreme in Y, so we infer that the sample probably came from Y. Now, there are two major fields in statistical inference, estimation and testing. Both of these fields extend the idea in the example we were just talking about. In estimation, we collect a sample and calculate a sample mean, and then based on what the sample mean is, we provide an interval of values that we claim contains the population mean. For example, a statistician might run a survey on income and find the average annual income in the sample to be $65,300. The statistician might then go on to publish a result about the population that looks something like the one shown here. This is an estimation in statistical inference. We calculate a sample statistic and use that one value to estimate a range of values for the population parameter. In testing, we actually start out with a value for the population parameter and then collect a sample and test this value against the sample. For example, you might assume that the proportion of people who prefer chocolate ice cream is 40%, but you then collect a sample of people and measure the sample proportion to be 32%. Based on the sampling distribution of the proportion, you conclude that your original assumption about the 40% proportion was probably not right. That is, the sample is used as evidence to test an assumption about the population. Now, of course, that is just an introduction to those two fields of statistical inference. Over the next two summary videos, we'll treat them in much more detail. But a good way to learn about estimation and testing is to get practice, so feel free to go to the PDISCO workbook, where you will find a huge array of in-depth questions on statistical estimation and testing. So that was sampling distributions. The key topics were the behaviour of samples, the sampling distribution of the mean, the sampling distribution of the proportion, and sampling distributions and inference.